From the Space Research Institute of the Russian Academy of Sciences. It'll be given by Dr. Petrosian, and it's entitled Vortical, Dynamo, and Turbulent Multiphase Flow.
Thank you. Before starting my presentation, I would like to express my gratitude to organizations of this interesting conference, because Topological Fluid Dynamics is unique conference. It includes pure mathematicians, applied mathematicians, biologists, computation, and physicists. So, outline of my presentation, I will first give some introduction and little bit explain what is mean field dynamics, and then I will analyze fluids with solid particles and fluids with gas bubbles, and conclusions. Okay, motivation of this work comes from analogy of magnetic field equations and vorticity equations. This analogy was pointed on very well-known review article of Kate Moffat, published in Journal of Fluid Mechanics in 1981 in special issue, which was edited by Batchelor and Moffat also. So, key question which comes when considering such equations is, everybody knows that in magnetic fields you have dynamo effect. If you have homogeneous turbulence with non-zero helicity, you will have always large-scale instability like dynamo effect and magnetic field generation. And it is well known in astrophysics and well acceptable. Then you have similar equations for vorticity. Question is, do you have any possibility again to have large-scale instabilities of homogeneous helical flows? This is long-standing problem, and there were some, how to say, of course, hypothesis or some suggestions that this formation is also maybe possible due to mirror symmetry breaking of homogeneous turbulence due to helical properties of turbulence. And this is long history. Initially, there was published very interesting work of Krause and Rödler, who showed that for normal neutron fluid without any rotation, homogeneous, if you have homogeneous helical turbulence, all perturbations are damped and you have just viscous dissipation. Then there was a series of work from group of Professor Moiseev from Moscow. They showed that indeed there exists possibility of large-scale instability if you just violate symmetry or break symmetry of Reynolds stresses. The problems of this work was that fluid flow and magnetic flow are very different. Magnetic flow is kinematic. You can put given velocity field and put magnetic perturbations. And when you work with fluid dynamics, of course you don't have kinematic formulation, because mean flow interacts with and there are interacting terms in Reynolds stresses. So it's quite difficult to put simultaneously homogeneous turbulence and symmetry breaking and perturbations, because if you break symmetry, you break on all fluid volume, and you break them on both in basic state in homogeneous turbulence and both for perturbations. But there was some good, how to say, achievements. William Frisch suggested special parity invariant flow and some multi-scale technique, which allowed him indeed to have alpha effect and to have non-trivial Reynolds stresses. But this was not, how to say, not turbulence. And there was other suggestion, which come from again group of Moiseev. It was published in Physica Scripta. This is misprint. This would be Y. And there was suggested another flow which displays non-trivial Reynolds stresses. This was homogeneous shear flow and homogeneous turbulence. Homogeneous, I mean linear shear. In fluid dynamics it's called, forgot name of this, coed flow. So turbulent coed flow was one of the good candidates to put simultaneously homogeneous basic state and perturbations and to compute Reynolds stresses. This is mean flow, turbulent coed flow, and this is normal, normal, well-known homogeneous tensor for correlations for homogeneous turbulence. It contains homogeneous part, and it contains helical part. And in this work, published in Physica Scripta, there was constructed special homogeneous flow, turbulent current flow with mean shear, which is linear, and with such correlation function, which contains normal, well-known homogeneous turbulence with helicity, and it contains anisotropic paths due to shear, interaction of mean shear with homogeneous turbulence initially. So then in this work was constructed very good homogeneous flow, which can be used for in mean field theory, and were calculated Reynolds stresses. These are anisotropic paths which were calculated by rapid distortion theory when constructing basic state. So then they considered homogeneous current flow, put perturbations, mean flow, and then put interactive terms, interaction of mean flow with fluctuations, and computed Reynolds stresses in linear approximation on mean flow. This is just perturbation equations, and these are Reynolds stresses. And what is more important, just show mean field equations, which contain non-trivial terms, including helical paths, and which is more important, it was found many partial solutions which show inverse cascades from small scale vortices to larger one, and what is also important, they found some numerical solutions also showing such non-trivial dynamics. And but what is interesting, this is how to say, some type of instability, which algebraic type instability. So perturbations are growing, and then they are dumping on infinity. Okay, in this part of work was found non-trivial, good dynamics with good initial basic state, and so on, with random perturbation techniques. Next question is, could we again find something with good initial unperturbed state and with which is, how to say, growing similar as in dynamo theory, like in astrophysics. And then again, we suggested two other systems with solid particles and systems with gas bubbles. Why we suggested such system? First, because in this system you can again use random perturbation technique in good way with justified basic state. And what is also important, there are many applications of such type systems in astrophysics and in environmental physics. This is first system which we are discussing. This is two fluid system. This is ambient fluid. This is fluid with solid particles. This is concentration of solid particles. And this is some divergence due to stock friction of one fluid with another fluid. So you can see that this equation is not divergent free. That's why you expect to have again symmetry breaking on Reynolds stresses. And also, which is important, this is not only non-divergent free, but it also don't contains no any non-homogeneities. So you will very simply have very good basic state, so that to put basic random perturbation methods. So again, we put some basic state, like it was done on previous work, but this is now not anisotropic, pure normal helical flow, like is written on books of Monin-Yagrom and in bachelor book on homogeneous turbulence. Then we put mean perturbations, and then put interacting terms, perturbation interacting with basic state, and again computing Reynolds stresses. Okay, these are mean field equations which contain some Reynolds stresses, this, for any. And we need to compute them, but algebra is huge, but acceptable. So these are the stresses which we want to analyze in field approximation. These are perturbation equations which we use to compute in linear approximation Reynolds stresses. And these are final equations. And you can see that final equation contain turbulent viscosities, of course, due to symmetry terms of correlation function, and non-trivial term, which look like term which appears in magnetic dynamo theory. And if you analyze the system, this system for vorticity, it becomes much more easier, and you may just find linear solutions. These are linear solutions, and you see linear growing mode like on dynamo theory for such type system, for system of fluid flow with solid particles, which, okay, for two fluids interacting with Stokes friction. Okay, there was another system for which we also try to find such type of non-trivial. This is system of ambient flow suspended with gas bubbles. And these gas bubbles are just, how to say, oscillating under fluid pressure. Again, this is Rayleigh equation describing radius of bubble. This is fluid for mixture, and this is density. But now we have one fluid equations. Description of bubbles is here. But we need little bit, so that apply random perturbation technique, modify these equations, this equation to write as equation for volume, because it gives better equation to make algebra. So just transform these equations for equations of volume of one suspended bubble, and then perform same analysis with subdivided mean flow, fluctuations, and put basic flow, and linearize these equations, and compute it all Reynolds stresses to see what happened. These are mean field equations. Again, this is alpha term. Okay, so what happened? These are mean field equations which we obtained. So again, in linear approximation, we obtained just same type of term, helical term, which gives you again large scale instability for such type small scale turbulence. So, and again, we may write equations for vorticity, and again it shows linear unstable modes. So to conclude, first, of course, mean field theory was extended to multiphase flows, but this is okay, maybe not as important. And some large-scale instabilities which are similar, like dynamo instabilities in magnetic dynamics, was observed in with using random perturbation techniques for flows with suspended solid particles and for flows with oscillating gas bubbles. Thank you.
Questions, comments?
Do I understand that you must have mean helicity in the turbulence to
Yes, of course.
effect?
Yes, of course. Like in dynamo theory.
Yes.
Yeah, sure.
Where do you think that mean helicity comes from in a shear flow?
For shear flow.
Well, or
Okay.
in shear flow.
On Monday, Professor Chitiani showed some experimental data. Mean helicity even exists in Ekman boundary layer, at least.
Right.
And I'm sure it exists.
So you have rotation, a rotating fluid as well, perhaps.
Okay, it may be due to rotation, yes. Yes. And of course, we did another study. We put both rotation and not rotating them and showed that rotation works similar as helicity. So, but this is another, maybe for another conference. Topological fluid dynamics, yeah.
Any more questions? Okay. Yeah, one back there.
Does this work? Could you do this for powder flows? There's
For what flows?
Powders.
Complex.
Powder.
Powder flow.
Powder, yes, why not?
Yes.
But this is very different. Powder flow is non-Newtonian
Okay.
fluid. But for non-Newtonian fluids, this is not challenging to obtain dynamo. This is more challenging for, normal fluid. But this is also some sort of, fluids with modified equation of state, but still Newtonian. For powder, yes, sure, why not?
All right, thank you again.